Welcome to today's webinar. The topic today is Grasshopper RFEM 6, design add-on control using templates. My name is Andreas Hörold. I am responsible for marketing and public relations in the company Dlubal Software. For instance, the content of the website, the webinars, newsletters, and so on. I will be the moderator today, and I will answer your questions together with Paul. Yeah, but my two colleagues can introduce themselves.
Okay.
Yes, hello. Sorry.
Okay.
Well, maybe Lucas starts as the order in the PowerPoint is.
All right. Yeah, hello also from my side. My name is Lucas. I work here as a customer support and product engineer, usually with the focus on the interfaces, and I will be your presenter today. Paul.
Okay, also hello from my side. I'm Paul Sivorgin. I support the product development in the area of interfaces, and today I'm going to answer your questions with Andreas.
Okay, thank you for your introduction. Then we can switch off our webcams so that the attendees can see the full screen. I say some words for the attendees who participate the first time, how you can ask questions. Yeah, you see the control panel on the right side of your screen. You can show that with that arrow here, and then you can enter the question here. And then we will answer you. If you don't get an answer during the webinar, maybe because there are too many, then you will get an email afterwards. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's all from my side. I hand over the screen to Lucas. Lucas, it's your turn.
Yes. Yeah, I think you should be able to see my PowerPoint right now. Let me double check it. Yes. Okay. All right. Thank you, Andreas. Yeah, welcome again from my side. Let me start with the content of today's webinar. It is divided in 4 points. I will start, as usually, with the introduction of the new features of the Grasshopper interface. With new, I mean related to our last webinar, which was in October 2023. I will continue with giving you a quick overview about the Grasshopper algorithm. Then relatively quickly switch to chapter 3, because this is the main topic of today's webinar, the connection to the Dlubal components. And at the end of the webinar, I will also plan to show you the basic Tekla components, or generally the idea to connect the Grasshopper algorithm or the file that we created, the structure, to multiple programs. Yeah, so let's start with chapter 1, the new features of the Grasshopper interface. Maybe as a short info, all these features that I will show here were customer wishes, so we heavily depend on your feedback, what objects we should implement next. So if you have any wish, or if you are missing some specific function, please let us know. We try our best to implement it. The first feature that I want to show here or introduce is a new component for the imposed line deformations. This was recently, I think 1 week ago, implemented. Additionally, the extension of the line and member load component with the input for line and member lists. Yeah, it's an alternative way to define let's say a load which is applied on multiple members or multiple lines, maybe because you want to have a trapezoidal load distribution. Then you can use a member list or a line list instead of a member set, for example. Additionally, we extended the imperfection case component with the option to create group of imperfection cases. And then the second page with one big topic, basically, we created also a new component for a set of members, a quite important feature in RFEM. And additionally, we also implemented a component for member set loads and member set imperfections. Yeah, these were the features which we implemented basically in the last 3 to 4 months. And now I would like to start with the presentation of the Grasshopper file that I prepared, or the Grasshopper structure. Yeah, therefore I switched to Rhino and Grasshopper, Rhino on the left, Grasshopper on the right. As I said, I plan to show you also the connection to the Dlubal components. And in this second chapter, I simply want to show what kind of structure do we have and how did I build it up. I will not model this live because it would take a bit too long. So I have, again, some kind of a steel structure or member structure with a stage, with stage beams in the center or in the middle plane, and then the roof consists mainly of these triangular truss members or truss beams, and everything connected with some kind of coupling members. I created the structure, of course, in Grasshopper via algorithm. While doing so, as you probably know, you can assign a lot of parameters or make certain dimensions parametric. So therefore I have these number sliders here. So here with this one, I can, for example, change the amount of divisions for my stage beams, or change the length of the structure, the frame height, roof height, frame distance, but also the frame count. Yeah. And how do I build such a structure up? I think it's quite easy. In general, I started in this case with a simple point. Then I copied the point, created a line in between, maybe divided the line to get the center node, did the same again with a new node on the top here, again created a line, divided it, and so on and so on. And then you take the nodes that you get via the division and connect them with additional lines. And this is in general the workflow that you use for beam structures. And at the end of the procedure, you get a couple of components, line components. Let me see, what else do we have here? Maybe these components and the polyline. And then you have basically you have one complete frame, yeah, of your structure, and you can take them and copy them into the Y direction in my case. Now, this is, as I said, not so difficult. The more difficult part is to set the data structure up in a way that you can easily reuse it afterwards. What do I mean with that? If I would do it, as I just said, take all these elements that I have highlighted here in green now and copy it in the Y direction via, for example, move component, then I would get all of the additional lines that you can see here in red as a result of one component. But that's not so ideal for me, because afterwards I want to assign cross sections and materials onto these lines. And I plan to use a different cross section for my coupling members as for my upper girder of the truss or the diagonals. And if I have everything in one component, as a result of one component, then I have to explode this data structure again and filter out the elements that I need for my truss, for my column, for my beam, and so on. So instead of doing it all in one component, I called it up multiple times. So here in that one, I have my stage beams. In this one, I have my columns, as you can see, and so on and so on. And I collected all of these lines again, put a name on it so I know what line collection do I have inside that curve component, and then build it or created this list here. Additionally, I also have here a point component which contains my points, where I will later assign nodal supports. So this is the work that I have done in advance for today's webinar, mostly just some small numbering parts that I will explain later. And the real modeling of the modeling of the Dlubal components and the connection of the Grasshopper components to Dlubal, this is what I will do now live. So how do you start with the Grasshopper, with the Dlubal plugin here? Maybe first of all, where do you get the plugin from? That's quite easy. You need RFEM installed on your PC. That's the easy job. You can download it for free on our website as a test license, for example. trial license, and then you can go to your program folder. I think Dlubal, select the version that you're using, in my case RFEM 605, go into the tools folder, and then here you have the Rhino plugin. And if you double click on this one, the plugin will be installed in Rhino and in Grasshopper. Okay, so after you install it, you have it here. And let me maximize it for a second. This plugin is divided in 3 parts. You have the model data components, you have the load data components, and let's say the export, import, and so on components. This is the grouping that we are using here. And regarding the logic, how do you start here? It's also quite simple. If you open RFEM, you have a project navigator on the left, or a data navigator, not project navigator, data navigator. And it's divided into basic objects, special objects, types for lines, members, and so on. Then at some point, the imperfections, load cases and combinations. And this logic you can also use in Grasshopper. Yeah? Just go through it step by step. You start with the materials, then you define the sections, maybe thicknesses if you use surfaces. If you do not have any surface, as I don't have anyone here, you can skip it, and then the nodes, maybe lines, maybe members, and so on. So I use the logic of RFEM also in Grasshopper. So I will start with the materials and sections. And I can define a material via the material component, which is this one here. And for the ones who follow us since a couple of webinars, just as an information, we extended this material component a couple of weeks ago, months ago, maybe even, with the functionality to define also user-defined materials. To do so, you need the additional material characteristics component, which you connect to this input, and you can define here your elasticity modulus, shear modulus, and so on, or even use it for orthotropic elastic 2D materials. But again, that's not what I plan to do now. I want to define a simple material based on our library. Yeah, in RFEM, we have a material library. And if you define the name here according to the name in our library, then it will create this material based on the library. Now, how can you define a name? The name definition is quite easy. You can use a panel, and inside that panel, you write the name. Now, ideally, as I said, you write it exactly in the way as we have it in RFEM 6, and you get the name in RFEM, or the exact name from RFEM 6. So if you open it up, maybe you have already a material defined, then you can copy it from the tables. You can see here S235, but the full name is including the code. Or you go to the CAD BIM navigator, you open the conversion tables, and here you can also select the material from the library, anything that you want, and you can copy the full name and paste it into Grasshopper. These are the 2 ways. If you use the way over the tables, please make sure that in RFEM 6 itself, in the program options, you have this full material description setting activated. Otherwise, it will only display you S235. This is not the full name. It will work if you do it like this in Grasshopper. But you can imagine that we have a couple of S235 materials in the library, and the export will basically pick the first one from our library that starts with S235, and you will end up with Cypress code-related steel material. So it's maybe not exactly what you want. So that's a bit of work to define. That is a bit of work to define the exact name in these components, because you need to work in combination with RFEM. So you could do this once, copy the names that you need from the materials and put it in a list. That's how I did it in the past. Yeah, I created a long list where I put all the material names inside, and then I picked always from one of these elements from the list and connected it. I think I have a bit better solution now. I'm using the value list now instead. So value list is also a component in Grasshopper. You have here a drop-down menu basically, and you can fill this value list with your own information by editing this value list, and you can see here the information inside, and you can write down whatever you want in here, and it will display this option here. And that's what I did with my value list here. I have here one for the materials, for the ones that I commonly use. And now I can easily use this drop-down function to select the material that I want. Quite easy solution, I would say. And the last thing that you, let's say, should do with the material component is assign an index number to it. Why is that so important? Well, I will show it in a second. Let me quickly do it. So now I created a material with the name S235, blah, 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 and the index number 1. Now the next step would be the definition of a section, cross-section. So again, I have a component here, and the logic is quite similar. I have to assign the section name. The section names can also be a bit complicated because of the codes or standards. So I did the same for the cross-sections, and now I can pick here from a nice list the section that I want. So I'm using here an HEA 300. And the other information that is required is the material index number. So that's the input that I have to fill. It is not the name of the material, it's a number. Yeah, in RFEM, when you take a look again at it, every material, if I create more, gets an index number, and our section component expects the number of the material. Now, if you assign the number to your material component, you can easily connect both components. Yeah, that's, let's say, the logical way, but you need to assign the number here. Otherwise, this material doesn't know what number it is, so it cannot share it with the section component. And of course, we should do the same for the section component. We should assign an index number because later on we want to connect it to a member component, and then we need the same logic or the same information again. So now let me copy this material 2 times. I think it's clear how it's working. And I need, first of all, material numbers section numbers 2 and 3. And then I assign here an IP 140 and an HEA 180. So, and that's all I need to do regarding materials and cross sections. Now we continue with the members. That's the next step. And for the members, I also have a component here, the member component, and the main input for a member is usually the line it is based on. And the line it is based on, I have here in, I have collected here, yeah, in that, yeah, let's say list. I want to show it again. This is now the lines for the upper girder and the lower girder, and I can connect it into the Grasshopper input of my member component. And the second required information is the section, and now I can connect the section component with the section start input of this member component. And now my member component has the minimum information that it needs. All right. Again, I want to assign a number to my member, because you can imagine later on you may want to apply loads onto this member. So when you do this, you need a member component load, a member load component, and the input here is the member number. So again, if you want to use this logic, you should assign a member number to the member, and this is also quite easy. We have here in sum 25 lines, so we need 25 index numbers for our 25 members, and I can easily create such a list of numbers with a series component. And I start with the number 1. Step is of course 1, and the count, this is basically the amount of lines from that component. I can use here a list length component. This will give me the number 25 again. So I get here now a list with 25 index numbers. Let me quickly show it. And these are the index numbers of my members. All right. Now I continue with the truss diagonals. So again, I need a member component. I take the lines from my Grasshopper component, the section from my section components. And I will continue with the numbering. Now, I use again a series component, but I do not start with the value 1 because I already used the index number 1. So what I do here is I take the last value from my previous series component. Yeah, this is taking the last value. I'm adding 1 to it. This is summary. And this is my new start value. And then again, I use the length of the list of lines and use it as a count. So this is the same logic again and again. And it's not really complicated to number the members. Yeah, truss diagonals, they have one additional option. We can also assign here via a value list the member type, for example. And the diagonals should be a truss member, so a member with hinges at the start and at the end for the bending moments. There are, of course, more options you can assign to members. You can find these options here in this more dialog or more button. For example, the rotation of a member, or applying a hinge or eccentricity, a member nonlinearity, or maybe even a comment. Okay. So far regarding that. Now to the columns. Same procedure again and again. This is a bit repeating now, but we need it. Otherwise, I cannot show the export afterwards. So let's do it a bit quicker. Connecting the section to the member component again. Same logic for the numbering. And yeah, that's it. And what I forget now, I just noticed it in all the member components. We have to make sure that we have to be careful when we are combining tree-like structures with lists. Yeah, that's a bit tricky part. In my case, I will simply flatten the incoming tree structure to get a list, and then it will combine both lists with each other. Yeah. That is something I have to do. All right. Now, regarding the coupling members, I use the same logic, member component, coupling members, and then THA 180. Again, I'm using here the value list to define a truss member. All right. And connected, of course, to the numbering. And then we are close to the finish of the member component. So one more for the stage beams. Grasshopper line. HA 180. Numbering. And that's it. Okay. Now, these are the members. I assign now to all of the lines members, but you can maybe imagine that for some parts of your structure, you want to use set of members. What could be an example? Maybe for the columns. Yeah, it's quite common to assign set of members for columns because it allows you to easier apply loads on it or imperfections. For example, you might want to apply an inclination imperfection onto your columns, and then you have to do it for all at once and not for each member individually. So that's one reason why you may need a set of member. Or let's say you want to apply a load, or even for the design afterwards. Yeah, let's imagine you design the upper girder of this truss member. It's not just a single span beam, it's maybe a single span beam where you have two additional supports, lateral supports that you may want to consider. Then you also have to design it as a set of member, and define the additional supports afterwards. So there are various reasons why you want to use set of members, and that's what I want to do here as well for the columns, and as I just said, for the truss upper girdle. So again, I need a specific component for that. It's not the member component, it's the set of member component, a new one that we recently implemented. And the logic is a bit different because a set of member in RFEM is made of, or is defined by the member index numbers. Yeah. If you define a set of member in RFEM, member set, new member set, you have to define, where's the dialog? You have to define the member numbers. So this is now a bit trickier in Grasshopper because first of all, you have to assign index numbers first, otherwise it's not so easy to define it correctly. In our case, we have them. Yeah, we have the member index numbers in our member components. Yeah, I can even show them. If I take a member component and I change it from assemble to extract, I can extract the information again that I just put in beforehand. And then with the panel, for example, I can show again the numbers that I assigned. So that's the index number of my members, which is nice because I need these numbers for my set of members. But what I also need is, let's say, my members grouped, yeah, because what I get out of my member component right now is a big list. It's a long list with one index for each member. If I would connect now this member component to my set of member or member set component, then I would get one big set of member, and this set of member contains all these members, which is not nice because I need a set of member for this column and one additional one for this, and so on. I do have these groupings in this Grasshopper component. So if I show this one here, you can see that this is not a long list. It's actually multiple lists where each list is on one branch of a tree. Yeah, that's what I meant before with tree-like structures. You have here, let's say, one tree, and each we have multiple trees, and one tree contains either 2 or 3 lines, depending if it's the columns in the front with 2 lines or the columns on the back with 3 lines. And ideally, I would have to apply this tree structure onto this list that I have here. Yeah, that would be ideal because then I could easily connect the outcome of this with my member set component. This is what I want to do, and I can show it here. Just give me a second. I will briefly explain it. Actually, it has to be placed here. So what I do is following. I take this tree structure that I just showed, yeah, where the curves or the lines are grouped in each, where every column is inside one list and each list is on one branch. Yeah. So this is what I have here, and I simply deconstruct this. Or I read the paths of these branches and apply this logic, this path that I get onto this unflattened tree component. So, and in this unflattened tree component, I take the list that I just got from my member component. So this is what I connected. I took this, oh, the wrong one actually. Wait, just a second. Yeah, that's the issue. Like this, I took the outcome of my columns component into this unflattened component, and I assigned this tree-like structure to it. I have to do one more step. I have to, let's say, how is it called? Trim tree component, and then I get exactly what I want. I have now here my grouping as I had it before for the Grasshopper curves, but now assigned onto my members. Yeah, this is my member information in here. And in here, I have also the member index numbers now. And this is what I can now easily connect to my set of member component. So I take it, I put it into my member numbers input in my member set component, and therefore I will get these member sets. Okay, what else can I define in this component? I can define here the member set type. We have two types, continuous member or group of member. I, of course, want a continuous member. And that is all for now. One more time with the member sets. For the truss upper girder, I have the same issue here. Truss upper girder, I again have here a list. And this list contains all the lines from all trusses. And I want to have this tree-like structure again, because I need it in groups and not all in one list. So I do the same logic again. I connect this component and therefore I drag it down here. I connect it to this component. And it will do the same again, I read the path from my tree-like structure. I assign it to my list of members that I just created. I untrim, or I trim this tree, this data structure, and then I can assign it more or less to my set of member component, but I have one issue remaining. And the issue is that this, let me show it. Where is it? It still contains the upper girder and the lower girder. I grouped this in one component before, but now I need only the upper girder and upper girder lines, and I still have all of them in one list. You can see every list contains 5 lines, so 1, 2, 3 for the upper girder, 2 for the lower girder, and I need to split it up. I only need the upper girder lines. So what I will do now is I take what I have here and I just use this split list component, and one list contains now the lower girder and one list contains the upper girder. Easy as that. And I take the the list B, which contains the upper girder lines, and I connect it to my member set component. And this is actually, in my opinion, the more difficult part in Grasshopper, to keep an overview about the data structure or to organize it in a way that you can easily reuse it. There are multiple ways, and basically you have to find the way that you can manage at best. Also important, member numbers, is of course the numbering of the set of members. I forgot that, so I will do it now. The same logic that I used before with the series components. So numbers, the type, let me reuse it, continuous member, and that's it. Okay. So far regarding the definition, I just noticed I have to flatten a couple of inputs here because I still combine tree-like structures with lists. Here it's not the case. Okay. Now, one more topic, the supports. That's also quite easy to handle. We have in our Dlubal link, of course, nodal supports. We have line supports. No, I just can't find them here. Line supports, surface supports, so all the options. In my case, I need the nodal support component, and the input is simply the node that we get from Grasshopper nodes, and then you have to define the spring values or the support itself, and make sure, if you don't know how to control it, move the mouse onto the input. We usually have a helpful info box that gives you the info. What do you have to enter here? For example, if it's a free support, then you type in 0. If it's fixed completely, then you use the string INF for infinite. Enter. or a value, and a value is then a string value for the nodal support. I fix my translations and also fix the rotation around the global Z axis. There are more options. Just to quickly introduce them, we have the possibility to assign nonlinearities, also including the friction component. We have many options to rotate the nodal support. A comment is also part of this input, so most of the things that you will need. I also have to say that we do not support all the features of every object in RFEM. So if I say we support nodal supports in Grasshopper, then it doesn't mean that we support all the functions from the main program. For example, regarding the nonlinearities, we do not support diagrams or partial activities, which is an option in RFEM itself. That doesn't mean it's not impossible to implement it, but so far these were the requests on us to implement such things. And if there are additional requests, we can of course also do it. Okay, these are the nodal supports. And now regarding the loading, I also want to quickly show you how you can apply loads onto your structure. And in theory, you would need a load case first. Before you define loads in RFEM, you need the load cases. That's also the logic that we show here in the data structure. It starts with imperfections, imperfection case, and then we define the imperfection, or we start with the load case and afterwards we define the loads themselves. So I want to skip this part and I want to define only the loads in Grasshopper. But how does it work in combination with RFEM? Well, that's where the template comes into play. We have the possibility in our export component to assign a template to it. The template file is an RFEM file which already contains a couple of information. And in that template file, you can save, for example, the load cases. You can save the load combinations already. You can save even materials and cross sections. Everything that you can save in an RFEM file, mostly, you can save in a template file. So I could even skip this part with the materials and sections if they are already defined in a template. And I have it here. I have a template where I already defined the load cases and the combinations and some other stuff that I will explain later. And I have to link this file to my export component. I will do it at the end. And then I can reuse these information that are inside this template. What does it mean for me in special? So if I define a member load component, I have to define as one of the first information, the load case number. So usually, if I would not use a template, I would create my load case here via Grasshopper. I would assign a number to it, and then I would link both components together. Now, as I said, I have it already in my template. Then, of course, I need to know the index number from my template, which load case has which number. That's the structure that I want to achieve at the end. So I know in my template, load case 1 is my dead load case. Then I have a live load case, number 2, wind 3, snow 4. So I have to be aware of this situation, of course, but let's say this is okay, I would say, as a situation. So I can easily assign here the index number 1 as an input for my member load. So this member load will be placed in load case number 1 or 2 or 3. Actually, I need the number 2, not 1. Should be part of my live load case. Now I want to apply it on certain members on my stage beams. I need the member index numbers again. So I connect my stage beams member component to these member numbers. And the rest can be done via a couple of value lists usually. So you define a value list component. You can copy it a couple of times already. And then you have to start the definition of the load. You define what kind of load is it. It's a force in my case. It is a uniform distributed load. The coordinate system should be the local coordinate system. And here also a hint, or the tooltip is here helpful. Yeah, if you use the local coordinate system, you have to type local as a string. And if you use the global or any other user-defined coordinate system, then you have to enter the index number 1, 2, 3. Yeah, then the load direction is local in set, and the load magnitude is 5,000 as a value, and 5,000 because we are using always SI units in our components. Also here mentioned Newton per meter or Newton meter per meter or bar. So this is why I'm using 5,000 instead of 5 kilonewton per meter. All right, this is the required input, and this will create me a member load. Now I do the same again for load case 3. For my wind load case, because I want to apply a member set load onto my columns, and therefore I need the member set load component, and it works in the same way at the end of the day. So load case number 3, it's again a force, a uniform one in my case. I assign it again to the local coordinates. Oh, sorry, no, I made a mistake. Member set number. Yeah, that's the mistake. Local coordinate system. Load direction is local and set, and the value should be, to look it up, 1,500. So 1.5 kilonewton per meter. And the member numbers, as it is a member set load, I get from my member sets that I created before for my columns. Oh, I made member set number. Sorry, there's again a small mistake somewhere. Load case force. No, it's fine. Okay. And one more time, because I also want to apply loads on my upper girder of my truss. So I can actually copy this component into load case number 4. Instead of the local coordinate system, this time I want to use the global coordinate system. As I said, I need the index number, and I want to use the projected lengths for my snow loads. And the load is 2.5 kilonewton per meter, and the index numbers for the member sets where I want to apply it on, I get from this component. So like that. All right. These are the load components, and I want to finalize this small chapter here with an imperfection on a member set as well, because this is a new component. They are still included into the model data group. I guess we will put it into the load group afterwards. Member set imperfection. And yeah, again, I have to define the imperfection case. I have only one in RFEM in my template. So that is the imperfection case. So I need to assign the imperfection case number. The member set number is again the ones from the columns. Member set number. And then again, the value lists for the definition of the rest. Imperfection type is an initial sway. Then definition type is relative. And coordinate system is again local. In local set. And the sway itself is 1 divided by 200. So 200 is this relative value that I input here. It's the basic value according to the Eurocode. You could optimize the sway. There are some, let's say, little bit more advanced formulas. If you consider the height of the columns and the amount of columns in one row, you can also, let's say, calculate a smaller value or a smaller sway. We have the inputs for that. I'm just not using it here in the webinar today, but that's also possible. And it's not only possible for the Eurocode, as you can see. We have also some parameters for other codes because they are calculated differently. Yeah, so make sure to check out these small info boxes here. All right, that is all I need to define for the imperfection. Now, one topic remains, and that is the design. We said in the beginning, the webinar is also about the design of members, basically, how to control the design. And you can find these design inputs in the member and member set components. Yeah, that's the member component. And under the design chapter, you have additional inputs. And we solved it not, let's say, we solved it in a let's say, more easier way for now. Because the only thing that you can do here now is basically assigning a type, an index number for a type. And what do I mean by that? Therefore, let's check again quickly RFEM 6 itself. If we deal with the, for example, steel design add-on, what do we need to do? We have to do the step to activate the add-on. We have to deal with the standards, according to which standard do we want to have a steel design? In case of Eurocode, which national annex? Then we have to deal with configurations for the ultimate limit state, serviceability limit state, and so on. And then again, we have a lot of options and checks that we, in theory, would have to control via Grasshopper, and these dialogues could be huge. So what we did now is following. We said the customer or the user could create a template in RFEM in advance, as we just did it for the load cases and combinations, or as I have it here. And he could also define in that template that the steel design is activated, the codes that he wants to use, and also things like types for the steel design. If you design, for example, this diagonal here, and you want to consider a stability analysis, you have to go into the design type tab, and you have to assign here an effective length type or a boundary condition type. This is the effective length method. That's the general method according to the Eurocode. You have to decide which one. And inside such type, you then define what are the nodal supports, where is this beam fixed, what is the buckling length, and so further and so on. And you can define these types in advance, as I did it here, and save them inside the template. And in Grasshopper, you only have to know, okay, what type is what exactly, and then use the number index for that. So in my case, for these, maybe not for this example, it's not so ideal, but for these truss diagonals, I could say, please assign here these steel effective length type 1 and the steel ultimate limit state configuration type 1. And type 1 for the effective length type is a simple single span beam. It's gable fork supported member on both ends. Buckling length is equal to member length. And by that I can also assign steel or timber design related settings onto my members already in Grasshopper. And I can do it also for the coupling members here, for example. So again, I use here the number 1 because this is also more or less like a single span beam. Stage beams may be similar. I make it quite simple here. The webinar, the goal is not to have it absolutely correctly designed. Yeah, it's just for showcasing what is possible. And regarding the member sets, for example, we could say, okay, for the columns, we simplify it as a single span beam, which is probably not ideal. But that's one solution. And I have to activate the design properties for set of members, because you have to decide if you want to design the member or the set of member. And if you do it for the set of member, you have to activate it. This is again the same thing that you would have to do in RFEM itself. Yeah, if you design a set of member, then you have to check this button, and this is the Boolean toggle that I just used. And for the upper girder, I could, for example, use now the type 2. I have 2 additional horizontal supports for the stability analysis. Yeah. All right. So just roughly, yeah, again, it's not the goal to design them absolutely perfectly. Okay. So now I just noticed that I also have here this topic in the set of members regarding the combination of a list, which I get from my numbering, and this tree-like structure that I explained before, where I have one list for each pair of columns, or set of column. And I have to be careful when combining these. Instead of flattening the member number input, which would lead to the fact that I get one set of member, not multiple, I will graft my numbering. So each list, each pair, or each set of columns will get one index number now. And I will do it the same again here. Okay. So that's the definition of the components. Now I have to export all of them, and I basically have to link all of the components that I just created to this input of RFEM, and I usually collect these components in a small data component before, because it's easier to move it around, I feel. So I link every component with the Shift button pressed on my keyboard into this small data container. Again, you don't have to do it. You can connect everything already with the export component, but yeah, I prefer split it up. Okay. Whoops. Maybe that's something we should do whenever a new component is created, directly link it to the export. Okay, that's one part, and the other one in here. You don't have to split it up, but this way it's easier to, let's say, deactivate, for example, the loadings, and just export the model data. Yeah, input. Okay, so now I have all my data in the input. I have to trigger the run of my component. I usually do it with a Boolean toggle. A button would also be possible. And then we have some additional options in here. And for example, I want to flip the z-axis, because in Rhino I'm using here a global z-axis up. In RFEM, my global z-axis is downwards directed, at least in my template. So I have to flip it up. Then I can define a name. Doesn't matter, name of my file that I want to create during my export. Then I also have to link my template that I have to this export component, and this template is saved in that path. I will simply copy it, put it into a panel, And of course, also including the name of the template file. So that's this ft6 file. Copy. And all right. Okay. So that's the name or the path to my template, and I link it to this input. And one thing that you should make sure is that the override functionality is turned off. So it's not possible to use this override set to true when you're using a template, because it's using following logic. When we start the export into a new file using a template, we will call up this dialog in RFEM, which should show up in a second. This one, you define the name, yeah, as I just did, and then we activate here the template functionality. We link it to the template that we are using. This is what I just did here. And this will mean that it's activating the add-ons, it's activating the standards and everything that I saved in this template. The new file will be created. And with this override set to true, it would mean at this point, it would remove everything again from my list of information and start the export. So everything in my template would be gone. So therefore, it's required to set this override to false, or I think the default is even false, just to make sure that you do not combine the override set to true with a template. That's not possible. Okay, now let me close this one here. I will also close this RFEM file because I want to export into a new file. Oops. All right, maybe on the left. And I hope I made no mistake. Otherwise, we will see some errors here. Let's try it. So we can already see there's some kind of connection established because it's reading data. RFEM is basically already blocked. I cannot select anything anymore. And let's see what will happen. Yeah, it's creating a new file. So far, so good. Yep, the structure has been exported. I forgot something in Grasshopper, but okay. So the structure has been exported. That's nice. We can quickly check it. Let me turn off the loads. We can see the structure, all the beams, all the cross sections have been created that I defined before. So that's nice. I also have my load cases in here and the load combinations that I saved in the template file. Yeah, I don't have to create it in Grasshopper because that's also a bit of work. And inside my imperfection case, I have the inclinations or the sway of the columns. And in my live load case, my stage loads, my wind loads in my wind load case on my columns, and yeah, some snow loads on my upper girder. So exactly what I planned to have here. Now, one thing that we could also do, which I, let's say, a little bit forgot here, we can also start the calculation of RFEM. Yeah, we have additional components here that allow me to run the export of allow me to run the calculation directly, starting via Grasshopper. So if the export is successful, we get here the output true. And if it was successful, we can connect it to this run component, to this calculation component, and it would have automatically started the calculation in RFEM. Now I have to do it afterwards again, which is not a big deal, but of course, it could have been in one step. It could have happened in one step. All right. Now let's wait for a second until it's calculated. No. I'm not sure what's happening now. Oops. Not exactly. Yeah, well, it calculated. Okay. I get my results now. Deformations, member internal forces, and so on. Exactly what I wanted to have. Not sure if I also got the steel design results. Let's see. Yeah, that as well. So yeah, that's what I also want to show. I can run the calculation in RFEM, and I also get the design results of steel design, because it was a part of my template, and I also feed it via these additional information in my member components. Yeah, so that's quite nice. And even though we don't have a specific component to import information back, what we could do is we could also run an export of the RFEM results into a table in CSV file, for example. So this will run the command to export the results of RFEM into tables, and then you can import the results back into Grasshopper, and you can do it via this read file component. I have to see where it is. There's some kind of component. I forgot where it is. But you can import, read file. You can import data from files back into Grasshopper via this component, and then you can filter for a specific result and maybe use it in combination with an optimization component like Galapagos to run calculation loops. So that's possible. I did it briefly in a previous webinar. If you're interested in that, maybe check it out. I have to skip here for today. Just one last topic that I want to show, a little thought that came up when I created this structure. I spent a bit of time in creating this line model here, yeah, and I have RFEM where I can connect it, or I have my Dlubal components which allow me to connect these Grasshopper lines to RFEM. Now, we're not the only software that has a connection to Grasshopper. Yeah, there's, for example, also Tekla, which also has a plugin. And the question is, why should I use now the direct interface between RFEM and Tekla if I can control both programs directly from Grasshopper? Yeah, if I already created a structure in Grasshopper, yeah? Why not use Grasshopper also to feed Tekla? And it's not as complicated. You can do the same thing again. Therefore, I have Tekla here now on my right and Grasshopper on the left, and I can simply use the beam component, for example, from Tekla and the profile catalog component to define a section, for example, the HEA 300. I can also select it from the catalog here, but the name should be fine. And by that, it will start to create the structure also in Tekla. And I can connect also the columns to this component. And you can see that we are building up the same structure again in Tekla. And let me do it a couple more times. One more time for the truss diagonals. I'm not sure. I think maybe we can even define the name directly. That probably also works. Yep, this is also working. And then one more component for the coupling members and stage beams. All right. And then you have your structure in Tekla already. Yeah, that's the same structure. And it's a live link, as you can see. Yeah, it will be updated directly. So same functionality for us if I leave it on true. And if I would change a parameter from the beginning, I would start the export process again. I will turn it off because it's slower than the one to Tekla. And I can modify my structure and it will be updated automatically in Tekla. So just a little thought that I wanted to share at the end. If you're using Grasshopper, maybe in combination with RFEM, or maybe with Tekla, please think about the idea to do it in both directions. Yeah, maybe to RFEM and to Tekla. Yeah. All right. Yeah. So far regarding me, I'm a bit over the time. Sorry for that. Anyway, I hope I was able to show you something new, maybe to give you some nice ideas for your project, or yeah. And then just let me say thank you for participating, and I hand it back to you, Andreas.
Okay, thank you, Lucas, for this nice presentation. We are a little bit over the time, but I would like to use the chance to show you the website where you can find the recording and the Grasshopper file and the RFEM model. Let me hand over the screen. Before I will turn to the website, just a small hint. If you want to book your free online appointment, such as a product demonstration or something like that, just contact our sales team with that link here, or you can scan the QR code. Also, if you want to get a non-binding offer for any product or any add-on. Okay, I turn to the website. Dlubal.com is our URL address. And under news and events, you can find the webinars. Those are the webinars of the next weeks. Next week, I will present news in RFEM 6 and RSTAP 9. I give an overview what we implemented approximately in the last year, new features, new add-ons, and so on. So then in the week after next week, we will present the add-on geotechnical analysis, then timber floor calculations, our regularly most frequently asked questions webinar that I present with Jürgen Teilmann. That's today's webinar. Yeah, it's also a previous webinar at the moment because we are over the time. That's why I click on it. So yeah, you will get an email in the next days when the recording is online with a link to that page. You will get also an attendee certificate. Then the recording will be online here in the middle. And then you can download, or you can already download the presentation slides, the Grasshopper file, and the RFEM model. Okay, yeah, that should be also all from my side. I thank you for your attention. Thanks to Lucas for the nice presentation. Thanks to Paul for answering the questions. I wish you all a nice rest of the day. I hope we meet each other in a future webinar. See you. Bye-bye.